ओके, तो स्क्रीन इज विजिबल एंड I'm audible, ठीक है। Okay, so in this series of gravitation, we have covered 9 lectures till now, and this must be the last lecture of gravitation. So today we are going to finish it, ठीक है। 10 lectures both होते हैं, means 10 hours we have spent on it. So it's good for you and good for me. So firstly, we will talk about the study that you are doing, ठीक है। How many of you are doing a study slot of 5 to 6 hours? How many of you? You can send the reactions also. I have enabled it for you. So Rekha, Ankita, Anand, Shivashankar, Suma, Priyanka, Shamila, Rajesh, every one of you. I'm asking this question to you, ना कि पढ़ाई अच्छे से हो रही, studies is going well. Okay, Suma has answered. So only one person is there whose study is going well. Huh? So what about else? What about others? You guys finding any trouble with the study? Huh? Okay. Manlinatham has no. Okay, okay, okay. Thumbs are up and another thumbs are down. So first of all, na, do not take stress. Okay. It is not a do or die situation. Everyone told you that it's a do or die situation. Just focus, ye and wo. So it will create some kind of stress. Huh? Do not take it on. Just try to think कि you are going to learn something new that you not know. Suppose Suma has answered first, so I will consider Suma. Suma, the age of Suma is around like 15 to 16 years. Okay. So if she will thinks in that way that in 15 years I have no idea about the how the satellite will move, what is the energy of satellite, and how we can give it, how the trajectory of a satellite is decided. Okay, so in 15 years he has no idea before that. Okay? But I have to, I get to know about this in today's session, in yesterday's session, in tomorrow's session. So that way of learning with the curiosity enables the neuron system in your brain. ठीक है, got it? So ऐसा नहीं होगा कि कुछ भी पढ़ना चाह रहे हैं with a stressful situation, with the stress in your mind. It is not, you are not able to do that. ठीक है? Even I also, when I'm in stress, you can't focus. I can't focus. The same rule apply for you because I'm human, you are human. You know, I think इस पे तो सब श्योर ही होंगे ना, you are human. I'm just joking. So we are with the gravitation lecture number 10, the final lecture. So in the previous session, the headings I have mentioned the same heading because I have give you a homework. Most of you guys are thinking that, oh, very good, the sir has forgotten about the homework. Sir is not talking about the homework. So most probably he has forgotten it. No, I have remembered it, but I know that most of you have forgotten. to do it. Huh? Is this so? Is this so? Huh? Tell me, is this so? So in today's session, we are going to recall, as this is the parampara that we are following. This is the tradition we are following. Then we have done with, we will do some gravitational potential. We find out gravitation potential due to different bodies. Most of the bodies we have covered in the previous lecture. But in today's session, only one body is remaining. That was the homework for you. But I'm very sure that most of you have attempted it. Okay. Okay, and it's good for you if you do so. And then we get, so Shamila has done it, na? So what is the result? Is it different from the previously got results, like for uniform solid sphere and all? Is this the same result? No, it is not. Then after we are going to, so forget about it. I will do it in today's session, and it's very good if you have attempted it. Thank you so much, and I appreciate it. So in today's session, we are going to do the same derivation for the ring. Then after we will go through the Earth satellites and the weightlessness situation and analyze it. After that, we will do a numerical problem, and that's it. Okay. And if we got some time, then we will chat. Okay. Then we will talk about ourselves, yourself. I will ask question to you. You will ask question to me. Okay. Got it? So do not left the meeting in the end, by the end of the lecture. Okay. So without wasting some time, let's just get started. So today we are going to recall the previous concept that we have learned. And what we have learned yesterday? The same, the gravitational potential due to different bodies. So in the recall part, the gravitation potential due to point mass we have covered. What is the gravitation potential itself? Gravitation potential is the potential energy per unit mass. Okay. Mathematically, it is defined as the work done by conservative force, negative of work done by conservative force divided by mass. And that is, of course, the work done by conservative force. The negative of the work done by conservative force is, of course, the potential energy. Okay. So gravitation potential is nothing but difference is delta U by M. Okay. So now the gravitational potential due to point mass, the formula for that is V is equals to minus of Gm over R. Okay, so this is a point mass, let's say small m, at this point P, at distance small r. What is the gravitation potential V at P? So Vp is equals to minus of Gm over R. Got it? Very simple. And this is a scalar quantity. Scalar quantity. Got it? Now, for uniform thin spherical shell, this uniform thin spherical shell we also known as the hollow, or I must write it, uniform hollow sphere. Okay, uniform thin spherical shell or uniform hollow sphere, same body. So we have find it out that the outside, if any point lies outside of it, and we have to find out the potential of that at that point. Suppose this is the uniform solid sphere. This is the center of it, and from the center at a distance small r, there is a point P where we have to find out the potential. So Vp here is nothing but minus Gm over small r. And it is because of our shell theorem that we have learned that any point lies outside the thin spherical shell will be considered. If a point lies outside the thin spherical shell or a hollow sphere, then you can consider that hollow sphere or thin spherical shell to be a point mass. Okay, and do the calculation. And so you can see that V outside equals to minus Gm over R, which is written here, is same as we have derived it for the point mass, minus Gm over R. Okay. Now, V inside the hollow spherical shell or hollow thin spherical shell, V inside is equals to V surface is equals to minus Gm over R, and we have derived it from this expression. Inside, like this point is P, and this is distance small r. We have to find out the potential at that. So what formula we have used? We have used dV is equals to minus E dot dr. We know that inside the thin spherical shell, this E is zero. Intensity is zero because at this point all the sum about the potential by this point mass, the intensity by this point mass. So the net sum of all of these will be zero. Okay, mathematically. So vector sum at this particular point, which lies inside thin spherical shell, the intensity will be net resultant intensity will be zero. So inside any point in this thin spherical shell, the intensity, the gravitational field intensity will zero. So dV is equals to minus AVTR. So E is equals to 0, which means dV is equals to some constant or 0, and dV is equals to what is dV? dV is the potential difference, which is V2 minus V1 is equals to 0, which means V2 is equals to V1, which means the potential remains same inside the thin spherical shell. And you know that the relation followed by it will be a decreasing, will be is decreasing like this. So at surface, you will see at surface, because this point P is away from the surface. Okay. So if you calculate the potential at the surface, so this R would become capital R, the radius. Okay. You know that V is directly proportional to 1 by R. So if R will increase, V will decrease. And if R decrease, then V will increase. So moving towards the center, R will decrease. So V will increase. You can see here. The V is constantly increase in negative direction because it is negative. Okay? This is V and this is R. Now what happens at the surface? It achieves the maximum value. Okay? And inside, the point just inside the surface, okay, the potential become constant. And at the surface, it has a value of minus Gm by capital R. Okay? This is capital R. So inside every point, the potential will be same as of surface. So this line will be a constant line like this. And this is the graph of it. Okay? And this value is of potential is nothing but minus Gm over capital R. Okay? Potential at surface. Got it? No. Uniform solid sphere. So V outside for solid sphere is also, you can consider this point, this solid sphere to be a point mass, and this point lies outside this. So the same expression for point minus Gm over R. But for inside, the situation has changed. The inside, we know that the intensity I, intensity inside the solid sphere is Gm small r over R cube, which means E is directly proportional to R. It is a linear relation. So intensity is not zero inside the solid sphere. So what the potential will not also be zero. Okay. Although the potential is all not zero in the previous case, but it is constant. But in this case, the potential is also varying, and it follows a relation of 3r square minus r square. V inside is equals to minus of gm over 2r cube into 3r capital R square minus small r square. This small r square is nothing but, if you consider a point P here at a distance small r, and you will draw a sphere touching that point, this small r is the radius from the center, or the distance from the center to that point where we have to find out the potential. Okay. Now, what is the graph of it? I have drawn for you. The graph will be, this is V. So graph will be, if you put r is equals to 0, which means at center, so the V at center is equals to minus of gm over 2r cube into 3r square. R square will cancel 2 power of it. Then V at center you will have minus of gm divided by 2, sorry, 3 by 2 gm over r. Okay, which is same as, you can also write it as minus of 3 by 2 V of surface. Okay. So initially V is following this relation. V is directly proportional to r square here, minus r square. This relation is a parabolic relation, quadratic equation it is. So quadratic equation has a parabolic variation. So firstly, up to the surface, it will vary as parabolically. Okay? And then after it will vary hyperbolically. Okay? Hyperbolically. This. So this point, from where this point is also named as point of concavity in mathematics, where the curve will change the concave of it. Here the concave is down, this part is down. Here the concave is up. So this point is also known as point of concavity in mathematics. So this is capital R, this is 0. Okay. This maximum value is minus 3 by 2 times V of surface. Okay. Got it? And V of surface is this. This is Vs. Got it? This variation is parabola, and this variation is hyperbola. So it is very important. Okay? Hi Yoga Lakshmi, how are you? So this is it that we have did in the previous session. So I hope you are clear with this. If you have any kind of doubt, you can ask. Okay? Anyone, any kind of doubt in these three types of situation? The uniform solid sphere, thin spherical shell, and point mass? Anyone? If any kind of doubt you have, you can ask. Okay? Now, the uniform ring. I have given you a hint in the previous session also, that for ring you have to consider the intensity and apply the relation in that and find the expression. Okay. So we know that the gravitational field intensity, which is E, for uniform ring, it is minus of gmx divided by r square plus x square raised to the power 3 by 2 I cap. Why I cap? Because this is the ring. This is the axis of the ring, and we have considered a point on the axis. Okay, this is point P. This is x-axis also. This is y-axis, and this is z-axis. So we have considered a point P here on the x-axis. That is why this intensity is in this direction. And we have also learned it from the previous sessions we have taken, that if you consider this mass to be dm, the field intensity will be in this direction from this. Sorry. attractive in nature. So if you resolve this, consider this angle to be theta. This will be a component and this will be a component. If you consider this to be a dm mass particle, just diametrically opposite of it, you connect it to the point P, then this is the direction of intensity. So you will see if this angle, same angle is theta, the component is again in this direction and in negative direction. So all the point, this is the first half, this is the second half. So all the point in second half will have a component just opposite to the component for first half. So this will cancel out each other. Only the resultant direction you will have in x direction. Okay, that is why we have considered the direction vector of I cap, which is the unit vector of x axis. Okay, now we know that. I hope you are clear with this. अगर कहीं पे भी समझ में ना आए ना, just ask it. ठीक है, do not afraid, do not hesitate, please. ठीक है, so we know the relation, we know that the dv is equals to minus of g, sorry, minus of e dot dr vector. Now dv is equals to minus, और minus यहाँ पे already है, and minus minus will become plus, so it will be plus gmx divided by r square plus x square raised to the power 3 by 2 dot. Now this dr vector we also consider only the dx vector, because we are only interested in the x direction. So this dr vector will result in dx, and dx vector को you can write dx I cap. ठीक है, this is the magnitude, dx is the magnitude and I cap is the unit vector. So ds vector you can write magnitude of it into the unit vector. Okay, so we know that this is also I cap dot I cap will become 1. So dv here is gmx divided by r square plus x square raised to the power 3 by 2 dx. Now you integrate it from 0 to small r to the point where we have to find out the potential. Okay, or you can set that here x is the only variable. Okay, so what we are going to do, we are taking out the g capital M and rest of it x over r square plus x square by into 3 by 2. Okay, we know that for simplification this is dv is equals to it's not 0 to r, integration of gmx divided by r square plus x square raised to the power 3 by 2 dx. Okay, now we are taking the potential from infinity to that point x, because what is the definition of potential? It is the work done per unit mass to bring a particle from infinity to that particular point, and that particular point we have situated at distance x. Okay, so this is the ring, let's say this is ring, this is point P where we have to find out the potential. It is at a distance x. So what we have to do, we have to bring a point mass particle from infinity to this point P. Okay, at a distance x from the center. So the limit would be from infinity to x. At infinity we know the value of potential, we consider 0. At x we have considered it v. So v minus 0 is equals to v. V minus 0 is equals to v. So v is equals to infinity to x gmx r square plus x square raised to the power 3 by 2 dot dx. Okay. Now v is equals to minus, oh sorry, gm, and you can take common gm. Okay. X dx. You know that the differentiation of x square is just above it. Okay. If you differentiate it, you will have 2x, and this x is here. So what you can do, you can take r square plus x square at z. Okay. And then do the same calculation. Okay. So we do not going into deep into that. I'm writing the direct expression, the direct result of that. Okay. So you can keep it in your mind. So v is equals to gm, the resultant of it, x over r square plus x square raised to the power 3 by 2. The resultant of it will be 1 upon square root of r square plus x square. Okay. The resultant of it. V is equals to gm divided by r square plus x square. So this is the potential at point P from the ring. This is ring. This is point P at a distance x. Okay. So this is the relation of it. Now, there is another method also. Second method, which is far more easier than it. How? What we are going to do, we are going a conventional method. Okay. Apply a conventional. We have considered a dm mass particle here at a distance small r. This r is nothing but it will be capital R square plus x square square root. You know that it is the hypotenuse of this triangle, and this is capital R. So we have considered a dm mass particle. Dm is a point mass. So what should be the potential? Potential will be very small, dv. So it will be g minus of g dm divided by r. If you integrate it, then you will have a potential minus g. This r will be fixed. So g by r you can take common. Integration of dm. Integration of dm is the total mass. So v, if you just add all the particles of dm mass, then you will have the total mass of the ring. So you can take that g capital M divided by r, and this r is nothing but minus gm over under root r square plus x square. Okay, got it? So this is the second method you can do. Got it? So I hope you are clear with this ring. Okay. If anyone has any kind of doubt, you can ask, and then we will move further in the lecture. Now we are with Earth satellites and weightlessness. Now, what are the satellites? Satellites are lesser mass object which revolve around a heavier mass. Okay, got it? There are two types of satellite. First is the natural and second is the man-made. Okay, so natural satellite, like our Earth has a natural satellite which is Moon, because Moon is lesser in mass and it is revolving in the gravitational field of Earth. So we can consider Moon to be a satellite, but it is natural. It is naturally made, because we do not made it. But if you talk about the all the satellite like Tesla, sorry, yeah, SpaceX is launching, NASA is launching, or also ISRO is also launching. Okay, so these satellites are man-made. So they are artificial satellite, we can say, which is also lesser in mass and revolving around the Earth. Based on the types of satellite, we have two category of satellite. First is the geosatellite, geostationary satellite, and second is the polar satellite. And let me just discuss it one by one. Okay. Now, Earth satellite. So any object which is revolving around a heavier mass object is considered to be a satellite. So here this object, ये जो object है, this is revolving around the Earth. So this you can consider to be a satellite. Okay. What are the uses of it? So we cannot use moon by our our conditions. So we cannot say that moon you should have to give us data about the situation going on pole, on the equator, what are the weather situations. So we cannot directly convey that message to moon. But you cannot say that moon is not useful for Earth. Moon is very useful for Earth. Okay? If moon goes, then the life will all Earth will also go on. Okay? Got it? So but we can command these artificial satellites, and the command that we give, the first is communication, live transmission, analysis of weather condition, and for geographical purpose. So these all are the uses of these Earth satellites or artificial satellites that we are using. We will use it for the communication purpose, the telephone, the mobile phone that we are using. We made call to our relative or any other person. So that is possible because of these satellites, the communication satellite. Live transmission of news, live news आती है तो वो because of the satellite is only possible. ठीक है? We can see the broadcast of one country to in our country, in our home, with the help of live streaming. So why it is possible? How it is possible? It is possible because of the satellites that are moving continuously. Okay. Also, the weather report will come in your mobile phone. If you are using a good mobile phone, I'm not uh, letting anyone down by saying that, but in today's that smartphone that we buy, so it's usually there is a weather forecast inbuilt in them, and they told us that today is a heavy chance of being rain. Okay. Today the day will be sunny from 6 to 7 p.m. Okay. So all these forecasts are made possible because of the analysis that is given by these satellites. Okay. So what are they doing? If they are at this position, they analyze the weather situation, they communicate this to this survey, and they will communicate to this point. Again, if it is here, it will analyze this position. So continuously it is analyzing the whole Earth or the orbit in which it is revolving and give us the analysis of that. Okay. Types of satellite, I have told you already, geostationary satellites and the polar satellite. Now, geostationary satellites. As the name suggests, you can see geostationary. Stationary means at rest, which means a satellite like this is the Earth. If the satellite is moving with the same speed of Earth, if Earth has an angular speed omega, and this satellite is also revolving with an angular speed of omega, so what will you see? You will see that this satellite is not moving because each and every instant it is there. Why? Because it is moving with the same speed. So we are observing the motion of this satellite from Earth, which means with respect to Earth, we are analyzing it. So velocity of this satellite with respect to Earth is velocity of satellite minus velocity of Earth. Now both are same. Both are same. So it will be 0. So velocity of satellite with respect to Earth will be 0. So this satellite will appear to be constant, to be in rest in the same position for you. Okay, like this. So it is moving with the Earth. You can see in this animation. This satellite is moving with the Earth with the same speed. So it continuously maintain its position same at this point. You can see this point. So all the time this satellite will appear at the same position. Got it? Now the satellite in a circular orbits around the Earth in the equatorial plane. This plane is the equatorial plane, and this plane is the pole plane. Okay? South pole, north pole, and this is the equator. And you can also say this is the axis of rotation of Earth. Axis of rotation. The satellite in the circular orbit around the Earth in the equatorial plane with the time period is equals to 24 hours. या तो टाइम पीरियड को पकड़ लो या फिर एंगुलर स्पीड को पकड़ लो. आई हैव टोल्ड यू बोथ. सो एंगुलर स्पीड सेम होगी तो भी ये स्टेशनरी दिखेगा. सो एंगुलर स्पीड सेम होने की वजह से इफ अर्थ इज कंप्लीटिंग its revolution about its own axis in 24 hours, then this satellite will also complete the revolution, complete this revolution about this orbit around the Earth in 24 hours. Okay? Which means it appears the same at same position because the time period is same. So these satellites are called the geostationary satellite. Okay? So appears to be stationary when viewed from a point on Earth. Now the time period of the satellite will be 2 pi Re plus h raised to the power 3 by 2 root gm. Do not confuse with this expression. Okay? Do not confuse with it. It is simple the Kepler's law. You can see if you take the square of it, this will be t square is equals to 4 pi square Re plus h raised to the power 3 divided by root gme. This will become gme. Okay? Then you will see that the t square is directly proportional to Re plus h whole square, and this t square is, if I consider this to be smaller, this is r cube. So this is nothing but the Kepler's law. Okay? So we have derived it from the Kepler's law. Okay? And I have also told you the derivation of it. Okay? Now, so if you keep this Re plus h as this, and we know the time period. So for t is equals to 24 hour, and we put all the values like capital G, mass of Earth, pi, and 4 we know. Okay? And we put t square as t is equals to 24 hours, then h, the height that we would achieve is 35,856 kilometers. So the orbit of this satellite, the geostationary satellite, will be of radius from, if you talk about from Earth surface, so it is 35,856 kilometers. But from the center of Earth, it will be Re, which is radius of Earth, plus h, which is 64,000 plus 35,856. You can add this. This is the orbital radius of this satellite. And what is this satellite called? This is called a geostationary satellite. Okay? So we use this for the purpose of telecommunication and mass communication. Mass means mass and media communication. So the INSAT group of satellite launched by ISRO is the geostationary satellite of India. Okay? INSAT. Remember this name. Now we talk about the polar satellite. Look, This is not a polar satellite, ठीक है, which is revolving around the pole. This is the equatorial position, and this is just perpendicular it the pole. So the satellite revolving around the pole, ठीक है, that is termed as the polar satellite. The altitude of the polar satellite is lower than that of the geostationary satellite. It is also, it is approximately 500 to 800 kilometer. Okay. And why we are using this geostationary satellite over too high, at too high altitude? Because what is happening, like the lower frequency signal like AM and FM, okay, so these are reflected by the ionospheres of our earth, okay. There are many sections of the sky, ionosphere, troposphere, है ना? So these signals are easily reflected by ionospheres, but for television very high frequency is there. So for that purpose, these frequency, these wave can penetrate into the ionosphere. So there are, most probably there are chances that these waves, which are the television wave, which are not transferred, which are not reflected by the ionosphere. This is our ionosphere. So this TV waves can penetrate into that because of their high frequency, so that we need a satellite so that it can reflect these, it can collect these frequency wavelength, frequency wave, high frequency wave, and reflect it to the center that we wanted. Okay, that is why the very high altitude is there. Now इसका जो रोटेशन होगा फ्यू आवर्स होगा इन सम टाइम, it is around 85 minute में it can, 85 minute it will take to complete one revolution of earth. So you can use it as the weather report, because we need the weather report very instantly, because in seas weather will change drastically अचानक से, ठीक है. So for that we need a very high speed satellite that can capture that, ठीक है. This satellite can view only small strip of the earth in one orbit. So the whole earth can be viewed strip by strip during the entire day. Okay? Because they are rotating at very high speed. So we can use it for remote sensing, meteorology, environmental studies, and weather analysis. Okay? Got it. The location app in your mobile phone powered by Google is the application of this remote sensing. Okay? So this is because of the satellite capturing us. Our devices is connected to a particular satellite, and if we move, the satellite will capture the movement of us, and it will give you the, in the, it will show you in the mobile application. Okay. Now, what is weightlessness? I hope you are clear with this satellite, na? If anyone, any kind of doubt you will have, you can ask. Simple hai, very simple. We have two kind of satellite. It is first it is geostationary satellite, and second is polar satellite. Geosatellite, geostationary satellite remains stationary with the Earth, which means the angular speed of rotation of that satellite is the same as the Earth rotation. And we can say the time period of the satellite to complete one revolution is 24 hours. So that is why it seems you as a stationary satellite. Okay? Because the relativeness is zero in that. Okay? It is to maintain that, to have a period of 24 hours, we need an altitude of 35,856 kilometers. One of the main reason to use that satellite is because of high frequency wave, which is useful for the broadcasting of television, okay? The video purpose. So for that we need these high frequency waves. But these high frequency waves can penetrate into ionosphere. Okay. So for that we need a satellite which is above the ionosphere and collect all these waves and reflect it back. So that is why we are using this geostationary satellite. Got it? Now, if I talk about the time period of it, it will be 24 hours. If I talk about the orbital length from the Earth's surface, it is 35,856. Now, if I talk about the polar satellite, it revolves around the pole. Okay? You can see in the animation also. This east-west are the direction, which is the equator direction, and this north and south are the pole direction. So it is revolving around north and south. Okay. But what is the application of it? Application of it is remote sensing, meteorology, environmental studies, and weather analysis. How it is possible for this this satellite? So it is possible because this satellite, this polar satellite, is moving very fast. It complete the rotation of Earth in 85 minutes, around 85 minutes. So see how fast it is moving. Got it? So it will give you a very small view, very small strip it can take. So that is why we have to make a very fast rotation so that it can complete strip by strip, so that we have a full view of the Earth. Okay. So this is it. Now we are in the weightlessness. Not we are not in the weightlessness. The topic is weightlessness. Okay. Now weight of an object. Weight क्या है? Weight is the gravitational pull. Okay, which is offered by the Earth to us. Okay. How the gravity will act to us in the form of weight. Okay. Suppose you have a weight of, so suppose you have a mass m. So the force with which the Earth will attract you is F is equals to m into g, and this is nothing but your weight. So try to correct one of the very incorrect statement that you are making from several years. And what is that? You will also say that if someone asks you that what is your weight, you will say it is 80 kg. No, 80 kg is the mass. So what is weight? Your weight is, if you are having a weight of, if you will say incorrectly that your weight is 80 kg, so it is incorrect. Okay, this is your mass, not weight. Now what is weight? What is weight then? So weight is mass into gravitational acceleration. So mass is 80 kg, gravitational acceleration you can consider 10. So your weight is 800 Newton. So that much force you are experiencing by Earth. ठीक है? तो जो जितना हैवी होगा उसे उठने और चलने में उतनी दिक्कत होती है, बिकॉज उतना ही ज्यादा ग्रेविटेशनल फोर्स इज एक्टिव. ठीक है. सो दिस इज द स्प्रिंग बैलेंस, जिसे हम तराजू भी बोलते हैं. दैट इज अ थिंग, स्प्रिंग बैलेंस. ठीक है. एंड दिस is a block which is having some mass which is pulled by the Earth by this force, so that the reading you will have on the string. In the free fall situation, what will happen if you will see? Okay. In free fall situation, like this is the mass, if this is the force acting on it, okay, and this is the spring. So if I just cut this spring from here, so this is free fall. Now what will happen? In free fall, the gravitational acceleration will become g. So if we talk about the net force on it, the net force on it will become 0. Net force on acting on it, only the gravitational force, which is F is equals to mg. So when an object is in free fall, it is weightless, and this phenomena is usually called the phenomena of weightlessness. ठीक है? So in satellite also, so हम अक्सर देखते हैं, we will saw the video, we have seen the video of inside the satellite, this person, we will say that they are in anti-gravity. No, that is not the case. If the satellite is polar satellite or geostationary satellite, then you will say that that person or that thing inside the satellite are in a free fall situation. They are constantly in free fall because there is no net force acting on that. Only the gravitational acceleration is there. Okay. This situation you will see. This is the free fall situation, not the anti-gravity. Got it? Although the gravitational pull is small here, but we cannot completely neglect the gravity. Okay. This is weightlessness situation. If you will talk about this, suppose there is a spring balance on which this mass is hanging. So initially this, if this is mass and these are the readings of it, initially it is showing this reading, let's say, and this reading is mg. And why it is possible? Because if you consider it to be a spring, which is also a spring, is also a spring. So what has happened? This mass is pulling the spring down. Okay? So this spring will get a reflection of it, applies the equal and opposite force on that. Okay? Which is equals to, because earth is constantly pulling it with mg. So the spring will pull down. But a spring will build a force which is spring force just opposite to this mg, which is kx. Okay? And that is why this meter is going down. Now the spring will extend at its nature from its natural length, and this is the natural extension L0. But what if the spring is cut down? If the spring is cut down, this end will move here, and this kx will become 0. Or you can say that when spring and this mass is free falling, that this kx is equals to mg. Okay? So the reading of the spring will become 0 because there is no factor, there is no ceiling now to stop it from the extension. So when you cut it down, this end will move in this direction. Okay? This block is also moving in this direction. So it will elapse this L node. It will cover this L node, and now the reading of the spring will become 0. So that is why we are saying that we are in a weightlessness situation. Okay? So I hope you are clear with this. So this is it from this chapter. Thank you so much for being attentive. If you have any kind of doubt, you can ask. Otherwise, you can leave the lecture. The lecture is being over. Thank you so much for being attentive. Bye bye. Take care. Keep studying.